In this random bits, I'm going to walk you through creating this snake game in Unity. Welcome back to another random bits. In this one I'm going to walk you through how I made this simple snake game in Unity. Now this is going to be a little different from some of my other videos in that I'm not going to actually code it with you. I'm rather just going to explain what I have done and walk you through the code. So first up, I've created the game as a very simple game. I didn't want to do any fancy graphics or anything like that. So I have, whilst it's a 3D game as such, I have set it to have the camera as an orthographic camera. And I have actually created all the main elements of the game, so the grid and the snake and all the tail pieces as simple quads. So if we actually have a look at the grid, we can see that it is a simple 20 by 20 scaled up quad. The snake is also a 1 by 1 scaled, slightly smaller than 1 by 1, so that you can see a slight outline. And the same holds true for the pieces of food and the segments of the snake's tail, which are simply a green and white quads. I've also set it up so that the grid itself is in Unity units of 20 across, and the snake actually moves in one Unity unit at a time, so keep things nice and simple. To get things set up properly, the grid is actually set at X and Y location of 10 by 10, so this makes this corner over here 0, and therefore I have moved the camera to location 10 by 10 so that it is sitting above the center of the grid. So that's pretty much all set up for the graphic side of things. There is a canvas with a simple text field for putting the scores in, and another object for some audio clips that we can talk about later. So the other key object that we have here in the game is a game controller. It's just an empty game object, and the main thing it has on it is the game controller script. And because it's such a simple game, I've pretty much stored all the logic in a single script. So we can see that this script has a reference to the snake itself. So the snake, the head of the snake, the red square that moves around. It has a reference to a prefab, which is the snake tail segment, and it's a prefab so that we can create new instances of it as we go. We can instantiate copies of it, and the same for the food prefab as well. And then because we are moving not a smooth movement, but move in a square at a time, what we have is how often we move in seconds. So every half a second we move. And then we've also got some logic, some values here to control how we speed up. So every time you eat a piece of food, we reduce your move interval by this value until it's, but we don't let it get any smaller than this amount here, so that you don't go flying off the screen. We also have the text field to update the score, and then a reference to each of the audio sources for some different sound effects. So one for when you pick up the food, one for when you die, and one as you move. And if we look back on this audio clips object, you'll see that is just an empty game object, and with a couple of other empty game objects with each of the audio sources on it. And I find this is a convenient way to do it because Unity doesn't let you put more than one audio source on a game object, but you can basically add as many audio sources as you want to any kind of empties. So this little structure here, it makes it easy to kind of manage all of that. So if we have a look at the actual script for the game controller, we can see we have the prefabs for the snake, the tail segment, and the food. They're just public variables. We have public variables for the movement interval in seconds, the speed up time in seconds, and the movement interval, the minimum interval in seconds. We also have that reference to the score and the reference to the 3 audio sources. Next up, what we do is we have a couple of variables that are used to keep track of when we're going to move and how often we're going to move. So the next movement time is actually the next time that we're going to move. And the reason we have that is that in Unity, your update method is called as fast as you can go. So often 60 or more times per second. And we don't want to move the snake each of those. So pretty much what we do is in this next move time, we store the time that we want to move at next, and then within the update method there is a check here to see if that current time is greater than next move time, and if that is true then we do all the movement logic, otherwise we just loop around. And then we have the current interval in seconds, so this is starts at our move interval time and reduces by speed up in seconds, and is used to calculate when we're going to next move after we've moved. Next up we have the location of the snake's head, in other words the red square, and because the grid is an even number of units or an integer based number of units, it's a grid. We can't really have fractional units of positions on the grid because we move one grid position every time. I'm storing the head location as a vector2 int as opposed to just a normal vector2. And in a similar fashion, I store the direction in which the snake is moving in a vector2 int as well. And so this is the direction that the snake is moving. So if this value is 0, then we're not moving on the x-axis. If it's -1, we are moving left on the x-axis. If it's +1, we're moving right on the x-axis, and the same for the y-axis, with 1 being moving up, 0 mean not moving, and -1 mean moving down the screen. So we start off by moving the snake up the screen. Now the trick with snake is actually, or the clever part of this game is actually these two things here. So pretty much as the snake moves, we know where the head position is, and the tail has to follow along with the snake. So effectively, as the head moves 1 step to the left, then all the tail's segments move 1 step to the left. But they have to remember where they were previously. So you can't just move them all to the left. They basically chase along after the head. And so the way we do that is with 2 lists. The first list is a list of the actual tails. So as we add new tails segments to the snake, we will instantiate these prefabs and add them to the list of tails that we manage, so we can have something to draw on the screen. And then the other thing we do is we manage a list of all the positions of those tails, and then as the snake moves, we shift those positions around and remove or move the positions of these tail segments so that the tail segments chase after the snake. Next up we have the current location of the food, and also the transform representing the food. So once again, that the current food object is instantiated using this prefab at this current location. And then the last 2 variables we have is the current best score and the current score. So we keep tabs on both of those. So in the start method, so when the game controller is created, so before the first frame, we call a couple of things. Firstly, we call the reset game method, and we call the spawn food method. So in reset game, have a look at that. All this does is it basically resets all the variables to a known state, or to their starting state, and this allows us. This is all broken out into a separate method, so that we can call that when the snake hits itself, and we want to reset the game as well as right at the start of the game. So firstly, we set the head location to the center of the screen at 1010. We set the direction that we are traveling in, so up the screen. We set the current interval in seconds equal to the move interval in seconds, so we reset it to our starting value of move interval in seconds, which was 0.5. So every 0.5 of a second we will move. And then we set our score back to 0. Lastly, we loop through the list of tail segments in our tails, and we destroy any of those we have. Obviously at the start of the game we won't have any, but if we reset in the game after it's been one round's been played, we'll have some tail segments, so we destroy each of those. And then we'll clear out the list of tail objects, or these tail game objects, and we will also clear out the list of tail positions. So that is everything that happens when we call reset game. And then the next thing we call is spawn food. So in spawn food, what we do is we choose a random X and Y location based on the size of the board, which is 20 units across, so anywhere between 0 and 19 we choose as a location for both the X and the Y. And we create a vector2 info from that, and we store the current food location. And then we create a reference to current food by instantiating a new food prefab. So we're going to create that object, and then we're going to position it on the screen. And where we're going to position it on the screen is going to be based on the location we calculated. So using current food location, we're going to do current food location.x and current food location.y as the location, and we don't care about the z value because it's effectively a 2D plane. We create a vector3 from that, and we also set the rotation to be identity, so no rotation because we're just going to be square. Now you'll see scattered around the code we have these little 0.5 f offsets. That's required because we want to center the squares that we're drawing, or the quads we're drawing, based on the cell. We don't want them at the corner of each of the units or each of the cells on the grid. We want to place in the center. So what we do is we offset from the grid location by 0.5, or in other words half a unit. And since our grid is 1 unit big on our grid, then that puts the quad in the center of the cell instead of at the corner of the cell. So if we jump back, we can have a look at that. If we zoom in here, you can see that we position in, if we just positioned it without that calculation, like where this is now, we can see the snake is at position 1010, it would appear right in the middle. Turn off gizmos, and so really we want it to be with this corner there and this corner there. So it's actually positioned at, say, 10.5 and y.5, and that will position it in the center. The other interesting thing, or thing that we do need to mention, is that because we're just drawing everything as a quad and they're all pretty much at the same z value, they could overlap and hide. The wrong one could hide the quad, so the grid might obscure the snake, or one of the tail segments might obscure the head segment, which is not what we want. So to avoid that, there's one or two ways you could do that. You could slightly adjust the z value for each one, but that has, because you're effectively then moving them away slightly, that's kind of tricky to get right. And whilst we have an orthographic camera, if we had a perspective camera, it would slightly shrink the objects that are further away, which might look a bit weird. So instead, what I have done is on the materials, if you look at each of the shaders, there is a render Q value. And over here, this number here allows you to adjust the order in which objects with that particular shader or material is rendered. So I'm using these unlit color shaders because we're just doing solid colors, and so we don't need any lighting, nice and proficient. And you'll see that if we have a look at the grid is set to 1999, whereas say the food is set at 2001, so that'll be in front of the grid. The snake tails are at 2000, and the head is at 2002. So it would go grid, then tails, then food, and then head in terms of the order in which things are rendered. And all of these are the same kind of unlit color shader, so each has just got a solid color there. So that kind of gets the game up and running, and now we can iterate through what actually happens every frame. So every frame in the update method, what we get here is a couple of things. So the first thing we're going to do is check our key presses and then change the direction. So we're going to look to see if the right arrow is pressed, or the left arrow, up arrow, or the down arrow is pressed. And if the right arrow is pressed, then we want to change the direction so that we are moving towards the right. And we do that by setting the vector, the direction vector, its x value to 1. So we're incrementing along the x-axis, and setting the y value to 0 because we don't want to move up or down. And we can do the same for the left when we go -1. If we're going up, then we set the y to +1 and the x to 0 because we're not going to move on the x-axis anymore. We just want to go on the y-axis. And the same thing for the down arrow, where we want to go move down on the y-axis. You'll also see there's these additional checks here. So in the game of Snake, if you're moving to the right, for instance, if you're moving to the left and you press the right arrow, you can't double back on yourself directly by moving backwards. So if the right arrow is pressed, we only want to actually change your direction to the right if you're not currently moving left. So that avoids you doubling back on yourself. And so it prohibits that. So basically, if you're moving right, you can only go up and down. If you're moving up and down, you can go left or right as needed. So if you're going right, you can go up or down. If you're going left, you can go up and down. If you're going up, you can go left and right, for instance. Right, so that deals with your movement, and that's checked every frame. So this actually introduces a small bug or feature. I'm not sure which one I wanted to call it, but pretty much because I check the key press every frame and can change your direction, it means if you're particularly quick or you're too quick, in other words, you press up and then right within the same frame, you may land up crashing into yourself. So really, as a player, you've got to press the up arrow, wait for your thing to move, and then time, say, pressing the left arrow to move left. And the reason I left it doing that is it means it adds a little bit of skill, but also if you only check the key press as you're moving, the Snake feels very unresponsive. So you would land up missing some of the key presses. So I went with this approach here, where you basically checking for the key presses every frame. All right, so that gets movement out of the way. So that means we can change the direction that the Snake is moving in. The next section of code, which we've already briefly looked at, or at least the starting part of that, is the decision around when to move. So as I said, the update method gets called at a high frame rate based on your hardware that you're running on. So it might be 30 or 60 or 100 frames a second. But we really only want the Snake to move at a regular interval, and it's moving that 1 unit every interval, and it starts up doing that at every half a second. So what we have here is this check here, which says if time.current time, so the time variable or object has a bunch of time related information. It tells you basically how long the game has been running, is what the time. So it's the time at the beginning of this frame. This is time in seconds since the start of the game. So it can be a fractional thing as well. And what we want to see is if the current time is greater than when we said we wanted to next move. If it is, then what we're going to do is we're going to update the score. So basically every move iteration, we just update the score. It's not hugely efficient, but it works. And then we get this piece of code. And this piece of code is probably kind of the crux of the game. So what we have is we have that list of tail positions. And every time we have if we have 10 segments in our tail, then we'll have 10 items in our tails position list, 10 vector two ints, the X and Y locations of each of the tails. And so what we're going to do is every time we move, we're going to take the current head location and put it at the start of the list. And then what we're going to do is we're going to drop the last position that we have in the list. And that effectively, what it does is it moves the whole list of positions for all the tail segments one along, and it also drops or sets the first position to where the head was. And so you get the effect that all the tail segments follow along on the path that the head has taken. And so it's reasonably simple. You just add the head location at the front, drop the last location at the bottom. So if we had 10 segments, we'd add the head location at the front, which now means we had 11 entries in there. Then we drop the one at the end, we're back to 10, but they've all been shuffled along one position. All right. Next up, what we do is we take the head location, which is a vector2 int, and we add the direction vector2 int to it. So that will either add 1 or minus 1 on the X or Y axis, or not change the X or Y value as appropriate. And we can just do that with some vector math. So that's nice and easy. And then the last thing we need to do in terms of moving the head is we want to see if we have wrapped or run off the edge of the board. So in this version that I've created, if you move off one of the edges, you come back on the other side. So if you go from the left, you show up on the right. If you go off the top edge, you come back from the bottom edge. And so to do that, we just check if your X location is smaller than 0, and if it is, we flip you back to your X location back to 19, or if it's greater than 19, we set it to 0, and we do the similar thing for the Y location as well. All right, so at this point in time, we've moved the head along, we've moved all the tail segments along, and we've wrapped the head location from one side of the board to the other, or the grid, if we've gone off an edge. All right, so the next thing we need to do is check if we've now, if the head has now run into one of the tails. And since we have a list of all the tail positions, this is pretty straightforward to do. So the first thing we do is we're just going to set a flag to say is dead, and we're going to set it to false. We're then going to loop through each of the tail positions in our list of tail positions, and we're going to see if the head's current location equals any of those positions, tail positions. And if it does, we'll set the is dead flag to true, and we'll break out of the loop because there's no need to keep checking if we've hit one of the tail pieces already. All right, so once we've completed this section, we'll know whether we've hit our own tail. So if we did hit our own tail, if that is true, then what we want to do is we will reset the game. So we will reduce the score, wipe all those, destroy all the tail objects, reposition the head back at the center of the board. We'll play our sound effect, our death sound effect. And then what we'll do is we're going to calculate our next move time. And rather than add our move interval, what we're going to do is we're going to add 2 seconds to that. And that has the effect of it basically resets the board, plays the sound effect, and then basically doesn't move the snake for at least 2 seconds. And that allows the player to realize they've died and understand what's gone on and that the board has been reset. And then the last thing we do is we update the snake position according to the new head location. So we set the head location X, the head location Y with that 0.5 F offset, and we just set the position to whatever the position is of the snake's object. Its existing or original Z value. And so we update it. And that has the effect of moving the little red quad that is the snake's head back into the center of the board because we've just reset all the variables. So that's what happens if you die. If you haven't died, or rather the snake hasn't crashed into its own tail, then what we want to do is we want to move everything around. So what we do is we calculate the next time we want to move. So we take the current time stamp, or the current time, and we add the current interval in seconds. So this is the value that starts at 0.5 seconds and gradually shrinks as we eat more and more food, so it gets faster and faster. And we calculate the next move time based on that. We then update the snake's position on the screen. So we move it to wherever the current head location is. And then we iterate through all the tails. So we loop through each of the tail objects, so the game object that represents each of the segments of the tail. And we set the position of that game tail segment to the value that we have in the array that matches that location. So the first or one at position 0 in the array of tails will be positioned at position 0 of our tail positions. So we're going to grab that X, we're going to grab the Y, and we add the 0.5F to offset it so that it's centered in the cell. And then we play the move sound effect. And the move sound effect I've chosen as a kind of thump, like a little heartbeat. And of course, because we play that every move, as our movement, our current interval in seconds reduces as we eat food, basically that little thump beat speeds up and up and up to add a little bit of energy and stress to the game by making a heartbeat that goes faster and faster. Right, so that's everything for movement. So we check if we've died. If not, if we have, we reset. If we haven't died, we move the snake around. Right, now for the last little bit of this logic, what we're going to do is figure out if we've hit or run into the food. And this is pretty easy to do. What we do is we check if the head location is equal to the current food location. And if that is the case, then what we want to do is we add another tail segment. So by calling this add tail method, and we're going to add that tail segment at the head location. So if we jump down to the bottom here, we can see what that does is it, in our list of tail game objects, it's going to add to that a new, it's going to instantiate a new snake tail segment prefab, and it's going to add it to the list of the tail game objects, and we're going to create that at the location with no rotation. So at the location that was specified here. And then the other thing we're going to do is we're going to, in our array of positions, we're going to add a position, record a position at this location, so that this new tail object should appear at this position. Right, so we add one more segment. So every time you eat one piece of food, you get a new tail segment appearing. We can then play the pickup sound effect. We then destroy the current food object, game object on the screen, and then we spawn food, which, as we saw before, basically chooses a new random location and creates a new piece of food. And then what we do is we're going to shrink the movement interval. I'll change the typo. Shrink the movement interval so that we can effectively speed up the player. So what we're going to do is we're going to say that the current interval in seconds is equal to this max function. So firstly, we're going to take our current interval in seconds and subtract our speed up in seconds. So if we look back in our game on the, wait for it to compile, on the game controller, we can see that we started moving every 0.5 seconds. And then when we speed up, we take away 0.01 of a second away from the current move interval. The problem is if you did that all the time, you would land up with a negative number or a number below 0, and you would just be moving flat out. So we need to stop it moving. We've got to add a limit to how fast you can go. And we do that with this minimum interval in seconds value over there. So looking back in the code, we calculate the current interval minus the speed up in seconds, and then we say that we want to take that value or minimum interval values in seconds, whichever is bigger. So if our current, which is what the max function does, so if our current interval in seconds, say, dips below or heads towards 0 or something like that, then it will never get smaller than min interval in seconds, because we're taking the maximum of either min interval in seconds or this value here. So that's our current interval in seconds. And then the last thing we do is we also say that if plus score, so in other words, we take the score and we pre-increment it, so we add 1 to the score. So that This notation means you've probably seen it normally go in score plus plus. That's a post increment. What we want to do is a pre increment. So we're going to say plus plus score. So that means it adds 1 to the score before it's used in the rest of this evaluation. So we're going to add 1 to the score, and if it's greater than best score, then we're going to set best score equal to the score. Okay, and then at that point in time, the update loop will fire again. We check the key presses. We look to see if it's next move time. If it isn't, we come back up to the top, and it keeps going on until next move time, until time is greater than next move time, and then it runs through that same logic again. And that's it. So it's quite a simple game, quite fun to make, and really the trick as such with the game is to have this list of positions that you keep adding and removing from, so that the snake follows its original path. Well, that's all I wanted to cover. Thank you for watching. If you like this video, please hit the like button. And if you want to see more videos like this, please subscribe. Also, the source code for this project will be available to my Patreons on my Patreon page. So if you follow the link below, you can help support the channel by joining Patreon and get access to things like the project's source code. So once again, thank you for watching. Cheers.